This next reaction is related to the Friedel-Crafts Acylation. This one is the Friedel-Crafts Acylation. So instead of an alkyl group, we're going to add an acyl group. So what is an acyl group? An acyl group is just some R group bonded to a carbonyl. So this right here. If we have this group bonded to a chlorine, this is considered an acyl chloride. And that's what we use in the Friedel-Crafts acylation. In our example, we have benzene and this acyl chloride where there's an ethyl group attached to the carbonyl. And as far as predicting the products for these, it's pretty straightforward. So all you really need to do is draw your benzene ring, and we're going to replace one of the hydrogen with the acyl group. And for example, here's this carbon that has the chlorine bonded to it. That's the carbon that's going to be attached to the ring. So that carbon will have the double bond O and the ethyl group, and there's the product. The byproduct of this is just HCl. One important feature of this, which is different than the Friedel-Crafts alkylation, is there's no carbocation rearrangement to worry about. So that makes predicting the products a little bit easier because you don't have to consider that. The mechanism for this is similar to what we saw with the Friedel-Crafts alkylation. We're going to use our acyl chloride. I'm just going to abbreviate the R group. And that will react with the Lewis acid, AlCl3. So we have the lone pairs on the chlorine, and one of those lone pairs will react with our Lewis acid to form the Lewis acid base adduct. Right, at this point, we're going to stick with what we did with the Friedel-Crafts alkylation, and we're going to lose this Cl plus as a leaving group to form a carbocation. So let's kick that out, and we end up with R, carbon double bonded O, a positive charge, plus AlCl4 minus. Now, we get this interesting carbocation here, which doesn't look all that great being on a double bond, but it's really not that bad. In fact, the reason we don't have to worry about this rearranging is because this carbocation is resonance stabilized. We have lone pairs on this oxygen, and I can use a curved arrow and draw the resonance structure for this. When I do that, I get a triple bond to the oxygen. So there's the second resonance structure. I should note that even in this first resonance structure, this is a linear molecule. It's not bent here, but I just drew it like that so it matched the starting material. So because of this resonance stabilized carbocation, there's no rearrangement to worry about. Now that we have our active electrophile, we can react that with benzene. So let's come over here to the bottom left. Draw in benzene. I'll react that with my active electrophile. Again, even though this is linear, I'm going to draw it bent just so that it's in the form that it will be in the final product. From there, we'll draw a curved arrow from the pi electrons on benzene to this carbon. Here I'll draw in the new bond to the C, double bond O, and the R. There's a hydrogen there, and a carbocation here. And then to get to the final product, we need something to act as a base. The easiest thing to do is to use a Cl from the aluminum tetrachloride. So what that will do is kick out a Cl-, which will come over here and take this proton and eliminate to reform the aromatic ring. So we get HCl, and we reform the catalyst AlCl3. So just to recap, like the other electrophilic aromatic substitution reactions, the first part was formation of the electrophile. The second part is the actual EAS reaction.